So we looked at the relation. We understand that this term is now actual actual humidity or absolute humidity, and this is the saturated level of the humidity. So the difference between the saturated vapor pressure and the actual vapor pressure is what is called the vapor pressure deficit. So we looked at how the variation now for transpiration to occur. I said the VPI is always going to be high in the saturated level. So we if this portion inside the leaf is saturated with water, then the only influencing factor over here is the vapor pressure in the atmosphere or outside the leaf. So when this value VPA reduces, what happens is this VPD will increase. So high VPD means the actual vapor pressure is low, and this is corresponding to a low RH, because we know the relation between RH and actual vapor pressure. So it's VPA by VPI. So if VP reduces, RH is also going to reduce. So low RH will result from a high VPD. Now, if this value is very high, what will happen is more water will keep going outside, because this is at a higher value and this is at a lower value. So water will keep going there in excess. So this is going to as a consequence of high transpiration rate, the stomata is going to reduce, because it will understand that there's a lot of water loss. The stomatal conductance, as a response to this high VPD, will start closing up, and then it will try to reduce the amount of water that is going. The same case when VPD is low, the actual vapor pressure is not, it is closer to the saturated condition, or it is lesser, but it is closer. So the conditions of high relative humidity is existing in the environment, and under such conditions the transpiration rate will be low. So because of this, the stomata is not going to be very responsive to it, because whatever is the transpiration rate is optimal. So at this level, photosynthesis will also occur efficiently. Transpiration is not resulting in a heavy loss of water. So as a result of which, it will be in an optimal condition. Now, transpiration, although we talk about it in terms of losing water, is a process that helps in maintaining the temperature levels of the leaf. So, transpiration is not a bad process, but again, the plant has to do some optimization to control the amount of water that is exiting the plant, as well as to keep the photosynthesis process from going on, because otherwise, because again, that is what is resulting in the manufactured food for the plant. But excess of water cannot be lost. Transpiration should happen, but it should not allow it to an extent where the plant is going to lose water immensely, and it is also having to balance the carbon dioxide concentration uptake. Now we talked about stomatal conductance. So one doubt that might keep coming into our heads is regarding the actual definition of stomatal conductance. So stomatal conductance is a rate, just like how transpiration and photosynthesis is, it is a rate. But we also say that it is the opening and closing of stomata. So how can we represent stomatal conductance with respect to photosynthesis and with respect to transpiration? So stomatal conductance, like I had earlier defined over here, is a rate of carbon dioxide entering or water exiting. So which out of it is stomatal conductance? So stomatal conductance is a process that can be represented in terms of carbon dioxide entering as well as water exiting through the stomata. So when transpiration is occurring, we know that transpiration is a product of the stomatal conductance and the vapor pressure deficit. Now here you can see that I have named this stomatal conductance as GSW. That means that stomatal conductance to the movement of water. Now we are segregating the two processes. So one is stomatal conductance to the water molecules. Here A is the assimilation rate or photosynthetic rate, which is a product of the stomatal conductance to carbon dioxide and the concentration gradient of the carbon dioxide between atmosphere and what is inside the leaf. Now, we know that um, carbon dioxide molecules are bigger than water molecules. It has a molecular weight of 44 grams per mole, a molar mass of 44 grams per mole, and water molecule has only 18 grams per mole. So the rate with which the carbon dioxide will be entering will be different than the rate with which water will be exiting the system. Now there is only one stomata. The stomata is open, and through that stomata, water also has to go out, carbon dioxide also has to come in. So in order to take care of this process, we have to somehow standardize this stomatal conductance. We have something called the diffusivity coefficient. So diffusivity is nothing but it is describing how quickly the molecules will move from a region of high concentration to a region of low concentration. So in the case of carbon dioxide movement, the region of high concentration is outside and the region of low concentration is inside. So the carbon dioxide is going to go inside. In the case of water vapor, the concentration of water vapor is higher inside the leaf and lesser outside the leaf. So it is going to go out. But again, like I said, water is smaller than carbon dioxide. So the rate with which, or the rate of diffusion with which, the speed with which this water molecule will go out and carbon dioxide will enter are different because of the size difference. So for this, the diffusivity of water vapor is found to be nearly 2.5 into 10 to the power 5 meter square per second at 25 degrees Celsius and 1 atmosphere at 1 atmospheric pressure, and a diffusivity of carbon dioxide is found to be 1.4 into 10 to the power minus 5. Again, because this one has got the rate with which it is going is going to be lesser in case of carbon dioxide and more in case of water vapor. Now, we say that carbon dioxide through the same stomata, say suppose stomata is just one opening, and through that opening, carbon dioxide will diffuse into the leaf 1.6 times slower than water exiting the system. So this can be found out by this law of diffusivity by Graham's law, which connects the diffusivity with the molar mass as both of them being inversely proportional to the root of the molar mass. So diffusivity again is a concept that everyone, most of them must have learned regarding the diffusion of gases. So here in our case, we are concerned about the diffusion of carbon dioxide and H2O. And here, by Graham's law, we get to know that diffusion or diffusivity coefficient is inversely proportional to the molar mass of the gas. So in that case, when we solve for carbon dioxide and H2O, we get that the diffusion coefficient of H2O to the diffusion coefficient of CO2 will be equal to the molar mass of carbon dioxide divided by molar mass of H2O, the whole root, from this Graham's law. And we know the molar mass of carbon dioxide is 44, molar mass of H2O is 18. And when you substitute these values over here and solve this, you will get something around 1.56. So it is nearly 1.6. So that is why we say that carbon dioxide is diffusing inside the leaf 1.6 times slower than water because of the change in the molar mass of these two particles. So this again can be translated to the stomatal conductance. So stomatal conductance is basically how easily the gases can move through the stomata. Since water has got a higher diffusivity than carbon dioxide, we know that water is a smaller molecule, carbon dioxide is a larger molecule. So water has got higher diffusivity. We say that the stomatal conductance to water, stomatal conductance towards water is 1.6 times the stomatal conductance to carbon dioxide. This means that for every, say if you're taking 10 units of carbon dioxide entering, 16 units of water is exiting. So for a particular value of photosynthesis, if we are going to lose 1.6 times the same concentration of water vapor with that rate of stomatal conductance. So if we can so if the stomata is say open like this and it is 5 micrometers, we can say that if the stomatal conductance is say GSC is equal to 10 uh, for carbon dioxide, then GSW is equal to 16 for to water. So from the same stomata, when 10 say 10 moles of carbon dioxide enters, 16 moles of carbon dioxide will exit the system. So based on this relation between the diffusion of carbon dioxide and diffusion of H2O. This one value is very important. The diffusivity coefficient of H2O to CO2 is always considered as 1.6, and this relationship is used in multiple regions when it comes to estimating the total conductance, the boundary layer conductance, and so many types of conductance that is resulting in these gases to be entering. So when before even we look into the gases at the interface of the leaf as leaf as the interface, the gases has to pass through some boundaries before it reaches the leaf. So during all of that, this diffusivity coefficient will be considered in terms of ratio of carbon dioxide water to carbon dioxide. It is equal to 1.6. So So we found out that the ratio of the diffusivity ratio of diffusivity of H2O to CO2 is uh, 1.6. Now in this equation, the vapor pressure deficit, like I said earlier, will be expressed in terms of millimoles of water per moles of air, because again we are concerned about the moles of water and carbon dioxide entering. So this vapor pressure deficit will be expressed in terms of millimoles of water per moles of air, and the carbon dioxide gradient will be expressed in terms of micromoles of carbon dioxide per moles of air. Now, when transpiration, as a result of this, when we get the units of transpiration, it will be in millimoles per meter square per second, and assimilation rate will be in micromoles per meter square per second. So, whenever we represent the rate of transpiration to some value in the x-axis, the unit of transpiration is always going to be millimoles of water per meter square per second, and unit of assimilation or photosynthesis is going to be in the units of micromoles per meter square per second. So will be the vapor pressure deficit, which will be the vapor pressure will be expressed in terms of millimoles of water per moles of air, and carbon dioxide concentration will be expressed in terms of micromoles of carbon dioxide per moles of air. So if we solve this equation with the units alone, we see that yeah, we see that if transpiration is in millimoles per meter square per second, then and vapor pressure deficit is in millimoles per mole, this millimole and millimole will get cancelled, and then GSW will be obtained in the unit of moles per meter square per second. So GSW is nothing but the stomatal conductance towards water. So from this calculation, here I have converted millimoles into moles, that is by multiplying multiplying it with 10 to the power minus 3. So 10 to the power minus 3 moles per meter square per second is equal to the stomatal conductance into vapor pressure deficit, which is in again moles per uh, moles per mole. So this moles per moles will get cancelled. 10 power 3 and 10 power 3 will get cancelled. And finally, we will get the unit of stomatal conductance to water in terms of mole per meter square per second. So from here, we are understanding that the unit of stomatal conductance to water will be moles per meter square per second. Now, in the same way, if you calculated for assimilation also, the assimilation is expressed in terms of micromoles per meter square per second, and the concentration gradient is expressed in terms of micromoles per mole. So here also we will get moles and the micromole and the mole getting cancelled, and you will get the stomatal conductance to carbon dioxide is also in terms of moles per meter square per second. So we understand from here that the units of transpiration will be in millimoles of water per meter square per second. Unit of assimilation will be in micromoles per meter square per second, and stomatal conductance, irrespective of whether it is towards water or whether it is towards carbon dioxide, will be in units of moles per meter square per second. So knowing the unit is necessary because again in modeling there will be a lot of estimations. So you have to substitute the quantities provided to you in the using the right units to obtain. We ultimately when you do the calculation you'll get some numbers, but what is going to be the unit depends upon understanding what each quantity is going to be, what unit each quantity is going to be represented in. So transpiration in millimoles, uh, assimilation in micromoles, and stomatal conductance will be in moles per meter square per second. Another unit conversion that we need to look into is the units of carbon dioxide. So carbon dioxide concentration is generally represented in terms of ppm, that is parts per million. It is nothing but parts per million means it's 500 parts of carbon dioxide per million parts of air. So 500 parts of moles of carbon dioxide per million moles of air means 10 to the power 6 moles of air. So that will be ultimately 500 micromoles per mole. So if you get a quantity, say we represent the concentration of atmosphere. So as of now, the carbon dioxide concentration in atmosphere is around 420 ppm. So when we say 420 ppm, it means that it is equal to 500 micromoles per mole. There are various models that have been also been developed to give a more robust association of stomatal conductance to the environmental variables and photosynthetic rate. And one such model is the Bolberry model. So in the Bolberry model, it is giving a direct relationship between stomatal conductance and photosynthetic rate, as well as the environmental variables like relative humidity and carbon dioxide concentration. So a bit different from what we had looked at yesterday. We have one particular equation for assimilation, one particular equation for transpiration. And transpiration is associated with humidity quantity. Assimilation is associated with the carbon dioxide quantity. So here what we are getting is we are getting the stomatal conductance as a function of or as dependent on photosynthesis, humidity, and carbon dioxide concentration. So all of that is combined into one entity called the Bolberry index, and then stomatal conductance will be connected to this Bolberry index through this model. So this is basically again giving us an idea how the stomata is going to open and close in response to carbon dioxide uptake and water loss through transpiration. And the model is nothing but a line that is a linear regression model that has been developed with the slope quantity, the dependent variable, the independent variable being this Bolberry index. You see here an into hs by cs is the Bolberry index, and then d naught as the intercept value. So this is nothing but an equation of the line in the format y is equal to mx plus c. So you can see here it is y is equal to mx plus c quantity, mx plus c. Here y is the stomatal conductance, m is this, sorry, this b1 term, c is this term, and the quantity x is this term. So this is how are we arriving at this line, and what are these data points over here is what we look into more in more detail. Yeah. So here, as you can see in this equation, this Ball-Berry index is the product of the net photosynthetic rate or net assimilation rate into Hs, which is the relative humidity at the surface of the leaf. It is not the relative humidity that you get measured directly from the weather data. It is the relative humidity at the surface of the leaf and the carbon dioxide concentration at the surface of the leaf. So in a field condition or an actual condition, when you look at a plant, the plant will be experiencing humidities at varying levels. Now, if you see the top leaves will be more exposed to the air as compared to leaves which are going to be somewhere in the middle of the canopy. So this is called canopy microclimate and it varies. So what we are focused on is what exactly is the relative humidity just above the surface of the leaf and not on all the layers that is very much above to the leaf. So the data we usually get from weather stations are the relative humidity data. So that data we will have to convert to the relative humidity at the surface of the leaf and multiply it with the net assimilation rate and divide it by the carbon dioxide concentration also near the surface of the leaf. So if we have the atmospheric carbon dioxide concentration, we will be able to find the concentration of the carbon at the surface of the leaf. So this term, the Ball-Berry index, is a product of AN into relative humidity at the surface of the leaf divided by the carbon dioxide concentration at the surface of the leaf. Now, suppose we are taking this Leica 6800 instrument that I had explained to you in the earlier classes and we are getting measurements of stomatal conductance and photosynthesis. From that, we will calculate this term AN into HS by CS and we will plot it in a graph like this. So you can see here, these black dots in this graph are indicating the measurements that were done on day 1. Then the white dots are the measurements that was done in day 2 and the triangular ones are the measurements that were done on day 3. And then we'll plot it we'll make a scatter plot out of this with the x-axis as this Ball-Berry index and y-axis as the stomatal conductance. So we'll get a scatter plot like this. And what we'll do is we'll do the least squares method. We'll apply the least square method or the linear regression model for each data set, day 1, day 2, and day 3. And we will find out the equation of the line that best fits these points. So the equation of the line is the line which will best represent the relation between the y-axis and the x-axis. That is what the linear regression model does. So the linear regression model here, what we are getting is the best fit line that is going to describe the relationship of the stomatal conductance with the Ball index or the Ball-Berry index. So in this equation, if you look at this term, which is a slope term, B1 is the giving us the sensitivity of the stomatal conductance to photosynthesis, and B0, which is the intercept, is giving the baseline conductance when photosynthesis is negligible. So same way, when we use this interpretation for the Ball-Berry, the intercept value is nothing but it is the baseline conductance. We know that from this graph, we know that GS is the y-axis value and Ball-Berry index is the x-axis value. So from this, we can know that the y-axis value when this x-axis is 0, that means when photosynthesis is 0. Now, relative humidity and carbon dioxide concentration is not going to be 0. So in that case, this x-axis will be 0 only if the photosynthetic rate is 0. So when the photosynthesis is 0, what will be the stomatal conductance is the interpretation of the intercept value in this equation. So the intercept in this is giving us the baseline conductance when photosynthesis is negligible or photosynthesis is 0. So when photosynthesis is 0, there will be some amount of stomatal conductance, that too to water vapor. So here the stomatal conductance is always the stomatal conductance to water vapor. It is not the stomatal conductance to carbon dioxide. So Ballbury is giving the stomatal conductance to the Ballbury index, the conductance to water and not to carbon dioxide. So what we are understanding is even when the photosynthesis is zero, the stomata will be open and some amount of water will always be going out. And depending upon the value of that intercept, it will be high or it will be low. So if the so if you see here, if for this line which is having a higher intercept and for this line which is having a lower intercept, we can see that the stomatal conductance when the photosynthesis is 0 is 0.4 and stomatal conductance when photosynthesis is 0 is 0.2. So this line will basically have more stomatal conductance even when photosynthesis is not taking place than this line. So this is going to lose more water in comparison to this line. And this line can be anything. It can be a plant, or it can be another leaf of a plant, or it can be another species, or it can represent the measurements like the data that we had seen earlier, measurements at a different time. So it can represent anything. Okay. So that is what the intercept is the value of the what does the intercept mean? Now, in this Ballbury equation, this ball index that you see, An into Hs by Cs, let us go more deeper into the unit of that. Now, this is the ball index, that is An into Hs by Cs. Now, we know that assimilation rate is always represented as the micromoles per meter square per second. So, that is the value over here. Hs is relative humidity. Relative humidity does not have any uh, it is basically a percentage value. So it is dimensionless. So we are not using any unit over here. And carbon dioxide concentration is in micromoles per mole. So when these two terms cancel and this mole goes to the numerator, we'll get the unit of mole per meter square per second. So the Ballbury index's unit is also mole per meter square per second. Y-axis value is also in moles per meter square per second. Now, when I say that the intercept is larger or intercept is lower, it means that for when is usually the photosynthesis very negligible. During in case of a C3 plants, during night time, the photosynthesis is going to be very negligible. So during that time, what is the stomatal conductance is what is being given by the this intercept value of the Ballbury curve. So if this red line is giving us a plant, a particular plant, and green line is giving another plant, we can say that plant one is losing more water than plant two. So this is again giving us information about the water use efficiency, how efficiently a particular plant is making use of water. And in this case, plant one is losing more water because of this leakage due to this minimal stomatal conductance that is still lasting even when photosynthesis is not existing. Now, what does the slope give? What information does this slope give? So here, if you see, we know that at say suppose this value is constant, Hs by Cs is equal to 1, and An is the only value that is varying, then at a value of 5 micromoles per meter square per second, this line is having lesser stomatal conductance than this line. So slope is actually for this line the slope is higher because as the slope becomes more steeper, the stomatal conductance value increases, and as the slope reduces, the stomatal conductance value reduces. So in this case, you are seeing that the brown line has a lesser slope value than the blue line, which is indicated that for the same photosynthetic rate, the stomatal conductance is higher for blue line than brown line, which is saying that stomatal conductance is more sensitive to photosynthesis in the case of the blue line than the brown line. So again, blue can be some plant or some another leaf or some other day's measurement, and brown can be representing another plant or species or whatever. But what the slope value gives us is the sensitivity of the stomatal conductance to photosynthetic rate. So here in the Bolberry equation, this value, sorry, this is B1. This is not, this is B1 and this is B0. Okay, so the slope is giving the sensitivity of stomatal conductance to photosynthesis, and the intercept is giving us the baseline conductance, so the stomatal conductance when the photosynthesis is negligible or when photosynthesis is not existing. Okay, so when I specifically stressed on the relative humidity and the carbon dioxide concentration that we are taking. The relative humidity is not the atmospheric relative humidity we are having. It is the relative humidity here at the surface of the leaf. Same in the case of carbon dioxide concentration also. It is on the surface of the leaf. So basically, when we have to measure the stomatal conductance, which is the rate with which this carbon dioxide is entering this, water vapor is entering the stomata, we also have to estimate what is the conductance or resistance that is offered to this water vapor. Sorry, carbon dioxide and water vapor. Suppose water vapor is going out over here, the total conductance is estimate the total conductance, not the stomatal conductance. The total conductance will be the sum of the stomatal conductance, which is the conductance from the inside of the leaf to just the surface of the leaf, and from the surface of the leaf to the air part. So this is what the total conductance will be. Till now we were looking at the stomatal conductance, but the total conductance will include what is the conductance of water from the inside of the leaf to the surface of the leaf, and from the surface also, if it has to go more above, there is a boundary layer that is existing through which the wind and all will play an important role, which will affect the movement of the water vapor to above. So total conductance will be the boundary layer conductance along with the stomatal conductance. Now, is it a sum of both of that? We'll look into it right now. Same is the case of carbon dioxide concentration. When carbon dioxide is entering the stomata, it has to cross this boundary layer, reach the surface of the leaf, and then go inside. So, total conductance of stomata or stomatal conductance to carbon dioxide will be the boundary layer conductance along with the stomatal layer conductance to carbon dioxide. Now, we have all learned about resistance, series connection, and parallel connection. So, this is also something related to that. I don't know why. Okay, this is also something just similar to that. We'll have a bit of physics in here now. Okay. So here what we see is when we had learned about resistances, we see that resistance in a series connection is total resistance is found out as a sum of the two resistance. And in parallel connection, it is found out like this 1 by R1 plus 1 by R2. This is this is the basic theory that is used wherever there is series and parallel connection. Even when it comes to in soil, if anyone of you are familiar with soil study, soil layers are stratified. So if the layers are in parallel layers, then how will the water move? Will be if it is in parallel way, the conductance or hydraulic conductivity is measured, is represented like this, and if it is in horizontal way in a series way, then it is represented like this. So in series connection, it is always the sum of the two resistance, and in parallel connection, it will be in this form. The same way, conductance is also like this, except that if resistance is the sum over here, conductance in a series connection will be in this format 1 by 1 by G1 plus 1 by G2, because the reciprocal of the resistance is the conductance. In excuse me, in evapotranspiration and all, the Penman-Monteith equation is making use of the surface resistance term. So when we are representing resistance, we can represent it as a resistance, but when you're converting it into conductance, you have to take the reciprocal of that value. So in the case of conductance, for a series connection, the total conductance will be 1 by G1 plus 1 by G2, and in parallel connection, it will be G1 plus G2. So in here, what we are having is it a series or a parallel connection? You can see that the resistance are going like this. Series means one after the other. Parallel means one above the other. So what is the conductance? How is the conductance over here connected? Is it a series connection or a parallel connection? Drop in your answers in the chat box, please. You can see from the diagram here, the red line and the brown line. Yes, that's right. It's series connection. So let's go back. Yes, right. It is series connection. So if you go back here, series connection, we see that the total conductance is 1 by G1 plus 1 by G2. Correct. All of you are right only. Manish, Mayank, Harita, Ryan. 1 by G1 plus 1 by G2. So in our case also, we can do the same calculation for the uh, boundary layer conductance and the stomatal conductance. So in that case, if GSW is the stomatal conductance of vapor through leaf, that is whatever vapor is going out from here, from the inside of the stomata to the leaf surface, that is the stomatal conductance to vapor over the leaf, and boundary layer conductance is given by GBW, then the total conductance will be this value. This is how I obtain this is nothing but 1 by GSW plus 1 by GBW. Now, when you GBW plus GSW divided by GSW into GBW, and if you take this to the numerator, it will come in this format. So this is how I got that equation. So the total conductance, which is to water vapor, which is the boundary layer conductance as well as the conductance of the water vapor from the surface into the leaf, or the leaf into the surface, is given by this equation because it is in a series connection. So what happens to the conductance of the carbon dioxide? You see that total conductance will again be conductance of the uh, stomatal conductance to carbon dioxide over the surface, and the total boundary layer conductance to carbon dioxide divided by sum of the stomatal conductance and the boundary layer conductance. But we know that the stomatal conductance to carbon dioxide is stomatal conductance to water vapor divided by 1.6, considering the diffusivity coefficient that we had studied in the last class. Water is a more smaller molecule, so GSC, I mean the carbon dioxide, will be diffusing at a more slower rate, which is again represented by the diffusivity coefficient. So you have to divide the water stomatal conductance by 1.6. In the same way, boundary layer conductance also has to be divided by 1.37. Now here it is 1.37 because in this layer only the molecular diffusion is being considered. But when you go upper and upper into upper layers, which is mostly the boundary layer, there will be some eddy diffusions and turbulent activities also. So those forces also have to be taken into consideration. And after all of that, the diffusivity coefficient that we are getting is 1.37. So same like how we are dividing the stomatal conductance to water vapor with 1.6, we will divide the boundary layer conductance by 1.37. And then we will substitute this in this equation, and we will get the GTC is equal to this in this format, GSW into GBW by 1.6. This is how you will get it in terms of the water's conductance. Now, why we need all of this is when we are estimating the surface of the carbon dioxide concentration on the surface, we need to know the boundary layer conductance to carbon dioxide also. So this is the way the Likert instrument, this I just wrote this equation here too, so that you can understand how the Likert instrument is estimating the internal carbon dioxide concentration. In the same way, it also estimates the carbon dioxide concentration on the surface of the leaf, and it is a function of this boundary layer conductance to carbon dioxide minus the rate of the transpiration into the ambient carbon dioxide concentration minus the net assimilation rate. So if the instrument needs to find the carbon dioxide concentration at the surface, it needs to know the boundary layer conductance to carbon dioxide also. And to know that, we should know the boundary layer conductance to water, which is then converted to boundary layer conductance to carbon dioxide and used in this equation to find the carbon dioxide concentration on the surface. So one part of the equation we found out. We have the AN, suppose we have the measurements for AN, we can estimate carbon dioxide concentration CS in just the way I told now. HS is nothing but the vapor pressure at the leaf surface to the saturated vapor pressure inside the leaf. Now, one change from what we learned in the last class is that this humidity is represented as the ratio of the partial pressures of water vapor on the surface of the leaf and in the interior of the leaf, not the mole fraction. So if we want to know the HS value, we should get the partial pressures of water vapor in air and partial pressure of vapor inside the leaf. And then in order to get the saturated vapor pressure inside leaf, this is represented as a function of the leaf temperature. And so we can estimate, if we know the temperature of the leaf, we can estimate this value. And on the surface of the leaf, if we know from the psychrometric chart in that gives us the values of partial pressures, we can obtain the relative humidity at the surface of the leaf. And then by dividing these two terms, we'll get the relative humidity at the surface of the leaf. So all these estimations, when we are talking about the Bolbury index, which is just a simple line equation, all these internal estimations are done, and all these estimations have been incorporated into the Bolbury model in BioCro software, where if we give the relative humidity value, the temperature of the leaf, the temperature of the air, the ambient carbon dioxide concentration, all of these values will be estimated, and we will get the Bolbury curve generated by the model.